Hey, everybody. Welcome to the last astronomy lecture of the semester. No fancy PowerPoints, no pretty pictures this time. I'm just going to talk for maybe 15 minutes or so about what are, in my mind, personally, as a scientist who's not exactly astronomer, but kind of peripherally connected to astronomy, what are the big, major unanswered questions for astronomy for the next few decades? And we just finished talking about two of the most important ones, so I'll start with those. Those are, what is dark matter? What is the deal with it? Is it little tiny particles we haven't detected yet? If so, what are they? Is it some kind of astronomical object that we haven't discovered yet? By the way, if you want to know my personal opinion for what the answer to dark matter is, I'm a particle physicist by training. So my answer is there's some kind of heavy particle with mass, but only weak interactions that space is full of, like neutrinos, but way, way heavier. And space is just full of those, and that's the mass that we see when we look at galaxies. Pretty straightforward. My guess is we'll find that dark matter particle in the next 20 years, but that's just a guess. And dark energy. Dark energy seems to be present in empty space, this energy that causes space to want to push everything away from everything else. Why? There are natural ways in particle physics to create what's called, it's a fancy term, a vacuum expectation value. In other words, the vacuum, empty space, doesn't have zero energy. It has some non-zero energy. There are ways to make that happen. In fact, one of the early pieces of research I did when I was still in grad school was looking at whether neutrinos could have caused a vacuum expectation value in the early, when the universe was very, very young, causing it to expand very rapidly at first. That research didn't go anywhere. But there are different ways in particle physics to create this energy in empty space. But we don't know in our particular universe which way is the way that's happening right now. So what is dark matter? What is dark energy, and why do they exist? And how do they fit into our picture of particle physics? Over the weekend, I realized that there's a bunch of stuff that I usually talk about in astronomy that we didn't get a chance to talk about because of the accelerated late start schedule that we were on. One of those things is I usually try to give just a little one-day overview of our modern view of particle physics. What particles do we know exist? What forces do we know exist? What are some of the unanswered questions in particle physics? And the dark matter and energy questions feed right into those, because if there's particles we don't know about, that changes our view of particle physics. If there's some kind of energy in empty space, that changes our view of what the forces are in nature. So these two things are very, very connected. And one of the reasons why I, as a particle physicist, consider them to be some of the most interesting questions in astronomy. There are lots of little unanswered questions in astronomy. Things like the solar corona problem. Why is the corona of the sun so hot? We don't know. But that's some little thing that'll probably get easily tidied up over the next 10, 15 years. As far as big questions, a lot of them happen at this interface between our theories of big, heavy stuff, like general relativity, and our physics of little, tiny particle size stuff, like quantum mechanics. And I think the next thing I would add to that list of big unanswered questions is, what is the deal with singularities? Why, when we take a whole bunch of matter and put it in a really small space, do our equations of physics tell us that that thing will have infinite density and collapse to a zero-dimensional point? That's kind of crazy, and it doesn't make any sense. So what is happening when a black hole collapses smaller than its event horizon and keeps getting smaller and smaller and smaller? Does its size shrink to zero? Probably not. That doesn't make any sense. But our equations tell us that it does shrink to zero. So I've done this a few times now. Let me grab my important books. This one and this one. We need to figure out a way to make our theories of gravity, which is Einstein's theory of general relativity, and our theories of quantum mechanics and quantum field theory play nicely together, so we can ask what happens if you put a star's worth of mass into a proton's worth of space. Right now, our equations just say infinity. Well, no equations. The answer can't be infinity. Infinity is not an answer. So What's at the center of a black hole? Is it a singularity or is it something else? What was at the moment of the Big Bang? Would you take the whole mass of the universe and make it smaller and smaller and smaller until it's the size of, this ball? Okay, take all the stars and galaxies in the universe and put them into this ball. What would happen? Well, its gravity would be so powerful that this ball would collapse into nothing. Really, though? Would it collapse into nothing? Was the Big Bang event a zero-dimensional singularity, or was it something different? Until we have physics that can deal with these two things on equal footing and at the same time, we won't have the answer to that. So a unified theory of physics that handles relativity and quantum mechanics in a way that plays nicely together has been the holy grail of physics for the past 30, 40 years. And we're not much closer now than we were in, say, the 1980s. If talking about the Big Bang, and now not just talking about the Big Bang theory that the universe used to be smaller and smaller and smaller, but talking about that Big Bang event, we can ask questions like, what caused the Big Bang? Does that question even make any sense? After all, the Big Bang event was not just the creation of a bunch of matter and energy in space. It was the creation of matter and energy and space and time. So it might not make any sense to even say the words before the Big Bang. The words before the Big Bang might be as meaningless as asking, what's north of the North Pole? If I go to the North Pole and then stand there and then go north, where do I go? Well, north only has meaning. North means towards the North Pole. Once I'm at the North Pole, there is no more north. Is it straight down at my feet? Is it straight up in the air? That's not north, that's up. North is a coordinate, or north to south is a coordinate system at which the North Pole is the origin. What is before? Before is a coordinate system. Time is a coordinate system at which there is some zero time. To ask the question, what happened before the Big Bang, is meaningless because there's no time before the Big Bang, because there's no universe in which events could happen. So maybe we just don't ask that. Well, can we not ask that? Our whole understanding of the physical world is based on cause and effect, right? This thing happens and it causes this thing to happen. Surely the Big Bang had to have some cause, something that made this expansion start. Well, does that have to be true? Does cause and effect apply to the universe as a whole? It applies to all the things in the universe, because the things in the universe exist in space and time, but the universe itself doesn't exist in space or time, or does it? Is there some outside space of time, some super universe, some multiverse? And we're not talking about Doctor Strange stuff here. We're talking about real physics. The idea that our universe is just one universe and there are other universes embedded in some higher dimensional space. That's a possibility. Is it a scientific theory? No, it is purely scientific speculation. And right now, that is where we are stuck, talking about the origin of the universe as a whole. Because until we have this unified theory of physics, we can't really say much about what would cause space and time to suddenly appear. So we really don't have any answers at all. We have ideas that we think might point us in the direction of an answer, but nothing that would qualify as a scientific theory. And that's okay. It's not okay for that situation to last forever, but it's okay for that situation to exist for a while. Sometimes when I'm bored or avoiding work, I know you guys probably all have stuff you do when you're avoiding work. I'll go online and I'll just argue with people about science. People who think scientists don't know anything. On their websites like Quora, you can go on Twitter, you can go on Reddit, and you can find all kinds of people who want to tell you that physicists and astronomers don't know anything. And there's one guy in particular, and on one site in particular, I won't mention his name, But he likes to post this list of unanswered questions about physics and astronomy. Say, see, physicists and astronomers don't know anything. Look at all these unanswered questions. Look at all these questions we can't answer. And my response is, yeah, that's normal. That is 100% how science works. Science works asking questions, looking for the answer, and if they don't have the answer, trying to improve their theories until they do have the answer. And this guy frames it as if that's some kind of dirty secret that scientists are hiding, that there are these questions that we don't have the answers to. And I'm like, dude, the only reason you know about these questions is because you picked up and read a science magazine where they're interviewing scientists, asking them, what are the unanswered questions? And there's nothing that scientists love talking about more than stuff we don't know the answer to. That's why they all became scientists in the first place, is to try to figure out the answers to things we don't know the answer to. There's a historian and philosopher of science. I'm getting a little bit off track here, but this is something I love to talk about. A very influential historian and philosopher of science named Thomas Kuhn, who wrote in 1968, I think. So maybe 65, 67. It's a little bit, this is a little bit older than me. So this is from the 1960s. It's called The Structure of Scientific Revolutions. And Thomas Kuhn paints a picture of how science works in practice. This isn't how science works according to the poster of the scientific method that you see in your elementary school and middle school science classrooms, where there's these steps, right? You have a hypothesis and you do make a prediction and you do an experiment and you analyze the results. And if the results don't agree with the prediction, then you change your theory. That's not really how science works at all. We saw some examples already in this class that point out that that's not how science works. We did experiments in the 1930s about nuclear beta decay, and we found that nuclear beta decay violated the conservation of energy. Did we say, oh, well, I guess the energy conservation law is wrong? We didn't do that. We made up some whole new particle that would keep energy conservation working. And luckily enough, we went looking for that particle and we found it. So this idea that as soon as something doesn't turn out right, we throw away all of science is completely wrong. And Kuhn says in Structures of Scientific Revolutions that there's always in science a certain background level of what he calls anomalies, just results that don't make sense. Questions we can't answer, experiments that didn't quite show what we expected them to show, little explanations that don't quite work right. And Kuhn points out that anomalies are expected in science, and figuring out why the anomalous results are anomalous is what scientists do all day. That is the bulk of doing science. He points out the fact that scientists are almost never trying to discover something new. Because what would it mean if you discovered something new? It would mean that your theories that you use to make predictions are wrong. We don't want our theories to be wrong. We want our theories to be right. What scientists are doing most of the time is checking as closely as they can to make sure all the predictions of all their theories check out. And where they don't, they try to tinker with the theory to make the predictions work. Kuhn calls this day-to-day work of science mopping up. In other words, just going back and dotting all the I's and crossing all the T's and making sure everything works the way we think it should work. But there's always some things that don't fit. There's always these anomalies, these unanswered questions. Kuhn refers to the task of answering those unanswered questions as puzzle solving. And that's what scientists do mostly all day, is solve little puzzles, trying to figure out why this thing works the way it does. So unanswered questions are not a bad thing in science. Unanswered questions are a necessity in science, because without unanswered questions, scientists don't have anything to do all day. Without little stuff that doesn't work quite right for them to check out, what do? Just pat ourselves on the back for E equals MC squared. Hey, we figured out all this stuff and it works perfectly. No, we've got a bunch of little problems we're always dealing with all the time. So this guy on the internet who thinks that it's somehow shameful that physics and astronomy has these big unanswered questions, he doesn't know what he's talking about. Those unanswered questions are it's what we get paid to do, is to go to work and answer unanswered questions. Now, the other thing Kuhn points out is very rarely in science we will reach a point where there are more unanswered questions than answered questions, and a scientific field reaches a point of what he calls crisis. And after a crisis, there is something called a paradigm shift. If you've heard the word paradigm shift to refer to anything at all, that term can probably be traced back to Thomas Kuhn's use of that term in Structure of Scientific Revolutions, speaking specifically about a shift in scientific paradigms where we move from one scientific theory to a new scientific theory. Paradigm shifts are rare by design. Every new discovery is not a paradigm shift. A paradigm shift would be like going from the geocentric system pre-Copernicus to the heliocentric system post-Copernicus, a major shift in our understanding of the world. The discovery of the Big Bang and expanding universe is a paradigm shift. These paradigm shifts of the discovery that all those spiral nebulas aren't in the Milky Way galaxy, that there are whole other galaxies separate from our galaxy, is a paradigm shift in astronomy. It requires completely rethinking the structure of the universe. Paradigm shifts are by necessity rare. Paradigm shifts were happening all the time. Nobody would know what was going on. So paradigms, scientific paradigms tend to last for a century or more. I don't think we're there in astronomy. I don't think any of these big questions that I'm talking about, figuring out dark matter and dark energy, coming up with a unified theory, maybe that would be a paradigm shift, but we've been talking about it for 40 years. It's not that big of a paradigm shift if everybody already knows we're expecting it. One thing that I think would be a paradigm shift, and I'll talk about this and leave it at that, one last unanswered question in astronomy, has to do with extraterrestrial life. How common is it? Are we alone in the universe? Are there other advanced technological intelligent civilizations in our galaxy? That's a two-part question. One is just how common is life? We could answer that in the next couple of years. Send something to Mars, bring back some rocks, find evidence of biological activity. There are microbes on Mars now, or there were microbes on Mars 100 million years ago, whatever. We could find stuff, microbes under the ice of Europa. We could find methane-based organisms in the lakes of Titan, whatever. But there are no intelligent life forms in our solar system for sure, other than us. So the question of how common life in general is, we could answer in our solar system. Or we could detect signs of life on planets around other stars. Questions of intelligent extraterrestrial life, what would we need to do in order to confirm such a discovery? We would need to actually receive a signal from an extraterrestrial civilization, either an intentional one or an accidental one. Find some sort of artifact of extraterrestrial origin. We have sent spacecraft out of our solar system. Pioneer, Voyagers 1 and 2, New Horizons, let's say a half a dozen spacecraft have left our solar system, and in 10,000 years will be maybe happening upon some solar system in some other part of the galaxy. If we found something like that, that would be confirmation of extraterrestrial life or extraterrestrial intelligence. The shorthand term for looking for intelligent extraterrestrial life is SETI, S-E-T-I, search for extraterrestrial intelligence. And we are engaged in a program of occasionally pointing radio telescopes at the sky and listening for signals from extraterrestrial civilizations. We have not found any yet. We probably will never find any. And the reason for that is not because I am pessimistic that extraterrestrial civilizations sometimes arise. Is because I'm pessimistic about how long they last. Our planet Earth has been here for around 4 billion years. Human civilization capable of radio astronomy has been here for 100 years, less than 100 years. So that's 100 out of 4 billion. That is less than 100 millionth of the lifetime of our star. If we look out into the galaxy and look at other potentially habitable star systems, and ask, what are the chances that their civilization and our civilization exist at the same time? Unless civilizations last for millions of years, that probability is going to be very small. There might be extraterrestrial civilizations that pop up somewhere in our galaxy relatively frequently. But unless the lifespan of that galaxy is astronomical timescales of millions, hundreds of millions of years, it's very unlikely that two of those civilizations will overlap for any significant amount of time. How long do we really expect human civilization to last? What's just think of civilizations in terms of like the ancient Egyptians, the ancient Romans, right? The Maya, the Inca, the Aztec. How long does a civilization last before sort of disappearing? 1,000 years, a couple thousand years, 10,000 years tops? Well, 10,000 years out of 4 billion is nothing. If civilizations last for 10,000 years and then go extinct, it's very unlikely that any two civilizations in our galaxy will be alive at the same time. Now, maybe the future is not that human civilization goes extinct. Maybe it's not that we screw up the planet with global warming until we all go back to living in caves and making tools out of stones and sticks. Maybe we will colonize Mars and create a space station on Europa and exist in our solar system for tens of thousands of years. Maybe we'll figure out ways to send spacecraft to Alpha Centauri and to nearby star systems. Maybe humans can figure out how to live for 100,000 years. One of my favorite astronomers, Carl Sagan. We've talked about Carl Sagan before, right? And I've showed you my Cosmos video. Cosmos DV connection, my Carl Sagan action figure. Carl Sagan made the point that discovering an extraterrestrial civilization would be important because it would teach us that life is common in the universe and that other intelligent life forms can exist. But it would also teach us something important for ourselves, which is that it is indeed possible for advanced technological civilization to last for tens or even hundreds of thousands of years without screwing up its planet and making it unsurvivable, everybody killing each other with nuclear war or whatever, that all of the humanity threatening or just running out of natural resources, growing in population so much that you strip the planet of natural resources. Finding another extraterrestrial civilization would be evidence that it is possible to outgrow this. Carl Sagan referred to it as a sort of planetary adolescence that humans find themselves in right now, and become grown-up civilizations in the Milky Way galaxy. So there's a lecture we didn't do where we kind of estimate how common we think life is in our galaxy using a bunch of, it's called the Drake equation. We didn't have time to do it, but suffice it to say, you estimate how common do you think habitable planets are? I think they're pretty common. How common do you think life is? I think it's pretty common. How common do you think intelligent life is? Not so sure. How common do you think intelligent life that lasts for hundreds of thousands of years is? That one's harder to estimate, right? Because we only have one example, and we're not always doing too hot here on Earth. So, am I confident that we'll have an answer to this unanswered question in the next 30, 50 years? I am not. But that doesn't mean we shouldn't keep looking. And I think that if we find even the simplest sort of life, microbes, algae, mold type organisms living on Mars or Europa or Enceladus or Titan or wherever, suddenly our picture of what sorts of life is possible grows exponentially. And suddenly our confidence that extraterrestrial life, at least the beginnings of it, is common, becomes very, very, we become very optimistic about that. We find 2 or 3 places in our solar system where there's life. Suddenly we would start to think, oh, there's probably life everywhere. If we don't, if 100 years from now, we've poked around under the dirt of Mars, and we poked around under the ice of Europa, and we haven't found anything, then we might start to get a little pessimistic. Well, maybe life is harder to get started chemically than we ever imagined. Maybe Earth is very rare. So this is an unanswered question that we might be looking at not 10, 20, 30, 50 years, like the first unanswered questions I talk about, but 100, 200, 1,000 years before we have any answer to that question. Okay, so I think that's all I'm going to say. One of the questions I sometimes ask on the final exam is, what do you think is the most interesting or important unanswered question in astronomy? So those of you who hung around until the end of the last video, maybe you get a freebie question in the final exam that you can start thinking about now. Other than that, I will post the video today. I will post the midterm exam starting on Wednesday, and you have Wednesday, I think Wednesday, Thursday, Friday, I said, to work on that exam. Good luck.